Hello, and thank you for joining us with Maths by El Profelo, doing some elementary number theory, looking from a textbook from James K. Strayer, working with linear congruences in one variable. Once again, this is actually right now chapter 2. Okay, we have our theorem on linear congruences and when they have a solution. All right, an important theorem to add now is our cancellation theorem. And that says that if CA is equivalent to CB mod M, and the greatest common divisor of CM is equal to D, then A is equivalent to B mod M over D. All right, and we're going to see where this helps us in solutions to simplify things. Okay, and that is going to help us in finding this x naught plus m over dn situation, right? Because when they exist, the solutions to ax is equivalent to b mod m are of the form of a particular solution plus m over d times n, where n is 0, 1, 2, all the way to d minus 1. Okay, so let's practice a few of these. So find all least non-negative incongruent solutions for each congruence, right? When it says non-negative, 0 is a possible answer. When it says positive, 0 is not a possible answer. Okay, so all least non-negative incongruent solutions. All right, so we solved this one in the previous video, but we're going to solve this one using our cancellation theorem. All right, so once again, we always need to come in here and double check, hey, what is the greatest common divisor of 16 and 28? All right, and so we know that that is 4, and we know that 4 divides 8. Because we know that greatest common divisor is 4, and we know that 4 divides 8, we can adjust our particular equation here and say, let's divide everything by 4. All right? So that would mean that we can actually solve 4x is equivalent to 2 mod 7. All right, that in order to solve 16x is equivalent to 8 mod 28, we could solve 4x is equivalent to 2 mod 7. All right, that's based on our cancellation theorem here that says that if CA is equivalent to CB mod M, right, then A is equivalent to B mod M over D. Right? Well, CM, its greatest common divisor is D, right? And we said over here that we had, hey, here is going to be essentially 4 times x, right, is equivalent to 4 times 2 mod m over d. Right? That's how it's kind of working through us, okay? So 4x is equivalent to 2 mod 7. Okay, and we can go through and in trying to solve say, well, does x equal 1 work? Well, clearly x equals 1 does not work. Then we can say, well, does x equal 2 work? Well, x equals 2 also does not work. X equals 3 does not work. But we do notice that x equals 4 does work, right? Because 4 times 4 is 16, and 16 is 2 more than 14, right? So we know a particular solution is x naught is equal to 4. We know that m over d is equal to 7. So all of our solutions will be x equals 4, x equals 4 plus 7, that would be 11, x equals 11 plus 7, that would be 18, and x equals 18 plus 7, and that would be 25. All right. So we have 4 solutions because the greatest common divisor is 4. When I divided all of these by 4, because 4 does go into each of these, I can simplify my problem. All right, so in the last video, we did it using the Euclidean algorithm. Here, we found our solution in a slightly different way, but we get to our least positive, or least non-negative incongruent solutions. How does it look for this equivalence relation or for this congruence? Well, if I come over here and I say, well, 12 and 54, what is that greatest common divisor? The greatest common divisor of 12 and 54, if we kind of think through things, that's going to be 6. And 6 does, in fact, divide 24. So what am I going to do? Does 6 divide 24? Yes. Does 6 divide 54? Yes. Does 6 divide 12? Yes. So I'm going to simplify this down using my cancellation theorem, and that's going to give me that 2x is going to have to be equivalent to 4 mod 9. Right? That's going to simplify my solutions down. My particular solution for this would be x naught is equal to 2, and my m over d, right, my m over d is equal to 9. So my 6 solutions will be x equals 2, x equals 11, x equals 20, x equals 29, x equals 38, and x equals 47. All right? Those are going to be my 6 solutions to this equivalence relation. I can double check that that's true, and watch. 12 times 47 is equal to 564. All right? And if I subtract, right, let's say 9 times 10, that's going to give me 474. And if I subtract 9 times 20, that's going to give me 294. And if I subtract 9 times 30, that's going to give me 24. Right? And what does that mean for us? That means for us that is what I'm expecting to have left over on division by 54. All right? You might say, well, wait a second, exactly how are you setting that up? Why doing it times 9? Well, let's come and do it the other way. 12 times 47, there's 12 times 47, 564. Let me subtract 54 enough times so that I have a remainder that is less than 54. And what do I see? That remainder of 24. So in fact, 12 times 47 has a remainder of 24 on division by 54. But we can simplify our calculations using this cancellation theorem, which is a very, very useful cancellation theorem. Right? And that cancellation theorem allows us to get to this solution form much more rapidly. Okay? I can always do these solutions using the Euclidean algorithm. All right? In our next video, we will solve these two congruences. Okay? Thank you for taking time with us. This has been Maths by El Profe Lo.